Okay, this is going to be the first in a couple videos I want to do in a series just talking about the file structures that we see in DOA5 and DOA5 Ultimate. Okay, I will be doing structure write-ups in a spreadsheet that I'll put up on my Google Drive that everyone can look at and contribute to. But I also feel that it's important to do maybe some visual analysis to illustrate to everyone my point of view of what's going on in the file, and also open up doors so other people can be like, you know what, man, I think you kind of saw that in the wrong way. Maybe this is what this means. So this opens the door to a lot of other things as well. Okay, so yeah, let's begin. In this video, I'm going to start off with the TMC file. The TMC file, you probably already know, it's the main model file that holds the data for the character files, stuff like that. If I had to make a guess, TMC probably stands for Tecmo Model Container. Okay. It's used not only in Dead or Alive, it's also used in Ninja Gaiden. In Ninja Gaiden, we see that TMC actually holds texture data, but in Dead or Alive 5 and Dead or Alive 5 Ultimate, the TMC is strictly model data. It does not hold texture data. The texture data is actually in a separate file called TMCL, but we'll talk about that later. So the TMC we'll get into right now. I'll jump into the hex editor. We'll break down the structures that we see in the TMC so that we are able to parse it and go through even making our own program. Okay. So as I describe this format, I want you to be aware that the way the TMC is formatted, it's using a basic block structure or a generic block structure that is reused over and over again throughout their files and within this file. So if I was to relate it to a different file, I would kind of relate it down to an XML file where you get a tag, you can define attributes, and then you can define data within the tag. Okay, then you can terminate the tag. So similar to that, we can define these generic blocks, and within these blocks we can define other blocks. So there's a hierarchy that can be created through these blocks. So it's an interesting mechanic they've created. Alright, so let's just give an overview of the TMC. I've got my hex editor here, and I've colored in 4 zones the 4 blocks that I can identify that are distinguishable. So we have the first block here. This is going to be our tag. This is going to be the block header. Okay. This blue stuff here is going to be the attribute data, or the information described for that tag, or whatever you want to call that block type. Then we have a offset table, and really all this is doing is just telling us where all the sub-blocks are within our file. Okay, and then the last section here is just all the raw data. These are all the sub-blocks that are included within the main block. Okay, so it's a very simple formatted structure. Okay, keep in mind that this is the Xbox 360 version. Everything is big endian. Even if it was the PS4 version, it's still going to be big endian. Okay. Everything here has to be written to a 16-byte alignment. So if a bunch of structures or something terminate and it doesn't meet the next address to meet it to a 16-byte alignment, it will fill it with zeros so that it's the next block coming after that block will be its address will start at a 16-byte alignment. Okay. So yeah, let's just start then. Okay. So let's discuss the header. Okay. This is the TMC header. The first 8 bytes are reserved for the string ID to identify the block type. Okay, in this case, it is TMC. It's the beginning of the header. Followed after that, we have some sort of flag system. It might have to do with some kind of hierarchy system. I'm not entirely sure what it does. We have a couple files here between Ayani and Kazumi. We can see that the 4 bytes here change. We have F011 over the F010. Not entirely sure what it does or what it means. We can see here in those sub-block structures, the flag is actually inherited from the parent structure here. Okay, you can see that repeat. Not entirely sure what it means. It's left as an unknown. Okay, after that we have the header size as a long value or long integer value. This just tells us the area of this green stuff. This is the entire block header. Okay. After that we have the block size. Okay, so from the beginning to the end of the block. Okay, in this case, the TMC is the file. It's the entire file. So this is relating pretty much to the entire file size. But again, to these subblocks that we have, that size would just encompass that block only within whatever block it was in. All right. Next, we have counts. So we have this first count here, 16, and then we have this other count here, which is 14. All right. So this is interesting. The first count here, 16, is basically describing or telling us that we have 16 subblocks within this main block, or within this block rather. And then the second count here is telling us how many of those blocks are going to be valid. So out of those 16, only 14 of those blocks are we going to use. The other 2 blocks are left as placeholders. We won't use them. They'll be ignored. So I'm not even sure why or how important that second count is. But the first count we'll be using to read through the table to get the subblocks. Okay. After that, there is a space, a null character here. This may be a third count that hasn't appeared yet. I'm going to assume it is. It's not a termination byte or it's padding or anything, I think. It might be a third count. Okay. Following after that, we have a offset. Okay. Typically, this offset is the same as the header size. It indicates the offset table of the subblocks that occur as directly after the header. So if I switch to another file here, not another file, sorry. Switch back to this for a sec. If I switch to a subblock here, which share the same structure as the main block there, you can see the similarities. You got the 4-bit ID, the unknown flag, you got the header size, and then after that, down here again, where the offset is for the offset table, this particular one is 30, meaning the offset table is directly after the header. However, if you go back up to this one, the offset goes beyond and actually goes to this address down here. So typically, directly after the header, typically we have the offset table, but in this case we don't. And we can tell just by doing a simple check or comparison, because there doesn't seem to be any other way of telling. Basically, you just do a logic statement here. If the header size is not equal to the offset table, then you know you have some type of information or data wedged in between that exists in that block. Okay, but just out of my research here, this extra block only seems to appear in the TMC. But yes, we can still do this thing, and or this check. It does seem to kind of relate to whole file as a whole. Anyway, we do need to read this blue data or this blue block here to correctly decipher the subblocks. Okay, so let's just break down, or actually, let me just ignore this blue thing and just complete the block structure here. So this thing, like I said, is going to go to a table. This is the subblock table. So this is just a bunch of offsets. And it's using this count up here, which is 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You notice that 2 of these are left 0. These are just placeholders. Okay. So you're going to have to do a check for that. If it's 0, then yada, yada, yada. Okay. Oh, which, by the way, the offsets that you get from the table, as well as the offset to the table, are relative to the beginning of that block that they are in. So if we were to go into a subblock, of course, any address that we get is relative to the beginning of that block. So this offset would be 40, which would bring you down to... No, this is 30. That would bring you down to here, which would then be 40, and that would be your data there. So yeah, these offsets we're reading here, they're relative to the beginning of the block, which in this case the TMC begins here. So the offset begins here. So our block for the TMC, its subblock here would be this MDL geo. Okay. But anyway, so that's it. That's the subtable or the offset table for the subblocks. So you can see here the first one is 170, and the first block here is that one there. Okay. So yeah, that's it. And this, of course, is all the raw data. All those subblocks are there. Okay. So now let's return back to this block here. Now this block is a little interesting. It's also very elusive. I'm not 100% what I'm about to tell you about it. So just have an open mind, and if you see anything, let me know for sure. Okay. So it begins with two shorts. We have 7 and we have 3. Okay. Followed by a long placeholder, a long integer used as a placeholder. Then we have a count and then another 0. This could be padding or it could be another count. I'm not entirely sure. Following that, we have a table. This is a string length table. So after this, we have a string table, and this is telling us how long each string is in the table. So in this case, it's saying the string is 13 characters long or bytes long. And then the rest are zeros because it's terminating to the next 16-byte alignment. Okay, now we're at the string table. Of course, as it said, the string is supposed to be 13 bytes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It is. We terminate to the next 16-byte alignment. Cool. Brings us to a series of floats. Now the floats themselves are a little bit confusing. They somehow relate to the size of the model. Could be a bounding box or something, but I haven't deciphered exactly what the data does or what it means. We can break it down. Let's say we have 3 repetitions of the floats. So we have 3 sets of floats here. Each set is 32 bytes. So this is the first set, the second set, and the third set. Following that, we have 16 bytes of data, which I'm not entirely sure what it does, but it pulls out values from the header here, or not the header, the previous sets of float data. So I'm not too sure on what that does. Okay. So anyway, we have that, and that brings us down to here. Okay. So now we have to take the count from up here, which is 7, and then loop for 7 times and read a long integer. So 1, 2, 3, 4, 5, 6, 7. And then again, of course, we terminate to the next 16-byte alignment. Okay. Now, I'm just going to quickly explain why these are all zeros. Let me switch this file just for a sec. This file came from the RAM. I dumped it from my RAM on my Xbox 360, and we can notice some changes to the files. You notice that we had a placeholder up here, and in the file that I brought from the RAM, there's now data present here, and the count will change here. It seems to be 6 when it gets uploaded to the RAM. It's a little odd, but in this state we actually have a low number. So if you look at any file that we actually extracted from the disk, it'll be between 4 and 3 or something like that. But as soon as you grab it from the RAM, it'll be 6, and we'll have some things written where we used to have zeros. So in my understanding of the format, they must upload it to RAM, and then they inject or link other files. So the whole idea of this structure is to be able to link to other blocks. All right, so that's what it's doing. It's identifying and linking to other blocks. But it's a standard block structure that's used over and over again, so it's very structured. Anyway, so yeah, these 000 that we reserved, actually down here, there's data that's inputted. So 1, 2, 3, 4, 5, 6, 7. Now, I'm not entirely sure what the integers relate to, but it doesn't matter because this appears after our file goes up in the RAM. So the game is deciding what to write here. We don't have to worry about that. So going back to here, don't worry about those zeros. Okay. So now we're at this this last little section here. And all this is telling us is what each subblock is. So the count for this one is the original count up here, which is 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, so it seems to be some sort of 4 bytes flag system. Okay, if the first byte here is not 0 or 80, then you read the rest of the bytes as a character code that is used to describe the subblock. So if it's not a signed file type or whatever, if it's a new type of file type, a unique type of file, you can actually inject it in here and then just give it a block name to whatever you want to call it. Like I can just put this as Mario or whatever. So I just defined a new type of block. Okay. But typically, if we have the flag 80, we are given an integer here called, or integer or byte here that's in this case 1. But 1 will mean that the first block will be an MDLGO. But if this was 1, then that means the second subblock will be MDLGO. So these IDs relate to what the actual block is. All right. So we can read through these to understand the order of what the block, or this, in the order the subblocks appear. All right. So yeah, in some of these where placeholders are, they're actually they have 00 in front of it instead of 08 or something. But it's hard to say exactly what the flag actually does. I can only identify 3 states of the flag. Either it's 0, 80, or not either of the two. That should be 2 states, but those 3 states, right? So I can see in this structure here, like I was saying, if it's not 80 or 0, it just defines it as a new character code here. In this case, it's EPM1. Okay. Anyway, going back to our original thing here. Yeah, so I let me just bring up this thing. This is the blocks that I've identified, like what each ID represents as it being an 80 flag. If it's 0, I identified these, but they seem to be outside of the realm of the 3D model. Might be pertaining to other stuff. 80 ones that have the flag seem to be solely dealing with stuff that deals with the model. Okay, so the last thing I just want to do to sum this up is just talk about the subblocks that we'll be getting into in a future video. Okay, so these are all pertaining to what makes up a character model. So we have model geo, which deals with the model itself. We have TTX, which is the texture header definitions for reading the TMCL. Okay, we have the vertex buffer, the face index buffer, the material buffer, the material info, which link the vertex buffer and index buffer, the skeleton hierarchy, which plays into the skeleton. We have the link header, which contains a bunch of linking IDs, which will link us to other files. Typically, it only links to one file, it links to the TMCL. Okay. We have the node. I don't know why they call them lay, but the node buffer, which has all the skeleton data in it. But these are all the same. We have more skeletons defined as a global matrix and a relative matrix. Then this one, CPF, I believe that is actually shader information for the sweat engine. These, I'm not sure. They may relate again to the materials. This one, I really seriously have no idea. Again, might be materials. All right. So these subblocks we'll be getting into probably in the order that they come, and I'll put up structures and stuff like that. Okay. But yeah, this is the structure of the TMC. Okay. That whole structure is pretty much a baseline for the rest of the structures that you see within the subblocks. But the subblocks don't have to be at this structure. You can define any block of random data, not starting with a typical block structure or a standard block header. Alright, so that's it. That's the TMC. Alright, please, if you guys see anything that catches your eye, let me know. I'll document it. Okay. I'll also put the link up for my Google Drive so you can look at it and add to it if you want.